This is a video on sampling methods. So first, what is a sample? A sample is a subset of the population. So there's some population that we want to know about. Maybe it's all US citizens, or all adult males in Missouri, or all seniors at Chaminade. There's some population that we want to know about. A sample is a group within that population, a subset of that population that we are going to study, that we're going to measure. The sample gives us a statistic. The statistic is the value for the sample itself. The population, though, has its own value called the parameter. So say I was studying all male adults in the United States, and I wanted to know their average height. The population of male adults in the United States has an average height, but I don't know what it is. So I take a sample of male adults from across the United States, and I find their height, the average of their heights, and that is the statistic. It's the value for the sample. In this case, the statistic is a mean, an average, but it could be a proportion, it could be a median, it could be a standard deviation. But there's some statistic for the sample, which is an estimate of the parameter for the population, because we won't typically know the parameter. So there's some population that we want to know about. We randomly select a sample from that population. We get the statistic for that sample, which we will use to infer something about the parameter for the population. Why do we take a sample at all? Why don't we just count every single person in the population? That would be called a census, when the sample is the entire population itself. That's incredibly impractical and expensive to be able to do that unless you have a really small population. And you're probably going to do it imperfectly. You're probably going to miss somebody or count somebody twice. And so we generally don't take a census unless, again, our population is small. We will typically always take samples of the population. And in the real world, that is generally what is done, because a sample is cheaper and it's much easier to accomplish, particularly in the amount of time that people in the real world generally have. So we use a sample to estimate the population. So are all samples good? No. No. Only well-drawn samples are good. Without being well-drawn, without being representative of the population as a whole, your sample could be biased. But what does it mean to be biased? Sampling methods that, by their nature, tend to consistently overestimate or consistently underestimate some value of a population are biased. The bias can occur in many different ways. It could occur from poor design of the sample itself or poor execution when you go to gather your data. Poor design could be convenience sampling. An example of that would be if I wanted to know people's opinions about the sport of football, and I go to the football game on Friday night, and I stand at the front gate and I ask people on their way in about their opinions of football, that's convenience sampling, because they're likely in support of football if they're at the football game. So I'm conveniently choosing a sample that's going to give me the results that I want. That's biased. Voluntary response bias is when the sample chooses itself. For example, pretty much any internet poll, like if you go to a website and it says, here, take our poll, then you're clicking on that and you're taking their poll. Well, you've chosen to be part of their sample. That's not random. That's not going to lead to something that's representative of the population as a whole. That's just going to lead to people who feel like they have an opinion to express. It's not going to get everyone across the board. It's just going to get the people with strong opinions. So the sample should never be choosing itself. That's biased. Or you could have undercoverage. So let's say you try to draw a good sample, but your sample leaves out some portion of the population that is fundamentally different from the people that are in your sample. Like if I am walking around a neighborhood in the middle of the afternoon, knocking on people's doors and asking them questions, well, if they're not home, they can't answer my questions. And the people that aren't home are probably similar to each other, and the people that are home are probably similar to each other in the sense that the people who are home are not working during the day. The people who aren't home are working during the day. So I'm leaving out a portion of the population that is fundamentally different from the people that are in my sample. That is under coverage. I'm not covering that portion of the population. That is biased. But bias can also result from poor execution once we've already decided upon the sample, and maybe we did a very good job of selecting our sample. But we can still have bias in the way that we go about gathering the data from that sample. There could be non-response bias or response bias. Non-response bias means I randomly selected my sample and did a great job of it, and it's representative of the population as a whole, but I don't get responses from a certain portion of my sample. I don't get data from them for some reason. Maybe I send them all emails and some portion of the population doesn't respond. And I believe that that portion of the population is going to differ in their opinions from those who did respond. Then I have non-response bias because I did not successfully get responses from a certain portion of my sample that I need in order to be representative of the population as a whole. Response bias is completely different. Response bias is when I am actually gathering the data, am I asking the questions in a leading manner that's going to lead them to a certain response that I'm trying to achieve? Am I asking the questions in a way that's going to intimidate them? So response bias is when we are gathering the data, are we manipulating the people that we are asking in some way? None of these are good. So how do we avoid bias? Well, we avoid bias first and foremost through randomization. We need to select the individuals from the population at random to form our sample. Randomizing makes sure that, on average, the sample looks like the rest of the population, that it is representative of the population as a whole. We want the sample to be representative of the population. So if our population has both males and females in it, we want our sample to have both males and females in it, and ideally to have the same proportion of males and females in it. If, as in this example, the population is 75% female and 25% male, I don't want my sample to be 75% male and 25% female. I want my sample to be representative of the population as a whole so that it accurately represents the population. While I might be determining the number of males that I need to get and the number of females that I need to get, I will use randomization to pick that number of males from the males in the population as a whole, and use randomization to pick that number of females from the females in the population as a whole. So we need randomization, or our sample is worthless and our data is worthless because it will not be ensured to represent the population as a whole. How big of a sample do we need? Well, you might think that if my population is the entire United States, that I would need a considerably bigger sample than if my population was just the people in the St. Louis area, for example. But that's not necessarily the case. It could be that a well-chosen sample of 100 people, which might work for the St. Louis area, could also, if I chose a well-chosen sample of 100 U.S. citizens, 100 people might be good enough in my sample. I may not need a bigger sample just because I have a bigger population. This illustration is meant to indicate that if I have a pot of soup, I could have a small pot of soup, I could have a big pot of soup. What matters is not the size of the pot of soup. What matters is how much I'm drawing out of that pot of soup to try. It matters the size of the spoon. If my spoon is so small that I'm not getting a representative sample of the soup, then it won't matter how big the pot of soup was to begin with. But if my spoon is big enough that I am getting a representative sample of the pot of soup, then it doesn't matter how big the pot was. I just need a spoon that's big enough to give me a representative sample. My sample needs to be big enough to be representative of the population as a whole. And it doesn't necessarily matter how big the population itself was. Make sense? Good. So how do we select a representative sample? We first have to choose a sampling frame, a list of individuals from which we're going to draw the sample. So if I am sampling people at Chaminade, I will need to obtain a list of the individuals at Chaminade or have some way of drawing a sample frame from the people at Chaminade. Once I have the sampling frame, I can choose the way that I'm going to select the sample randomly. I could use a simple random sample. A simple random sample is a sample in which each set of some number n of individuals in the population has an equal chance of selection. If I'm drawing a sample of 100 people, then every possible sample I could make of 100 people has the same chance of being chosen. So a sample of 100 people over here has to have the same chance of being chosen as a sample of 100 people over here. Every possible sample I could conceivably make of 100 people has to have the same chance of being selected. That's a simple random sample. A stratified sample is when we recognize that our population has different groups within it, and we want to make sure that we get representation from each of those groups. We call those groups strata. And so we break our population into strata, into groups that are fundamentally different from each other in some way that matters to us. Maybe it's males and females. Maybe it's kids, teenagers, adults, and senior citizens. And we want representation from each of those. Maybe it's teachers in the English department, teachers in the math department, teachers in the theology department, teachers in the science department, teachers in the social studies department, and so on. Those are our strata, and we want to make sure we get representation from each of those. So then we break our population into those strata, and we randomly select members from each of those strata. We take a simple random sample from each of those strata. It could be that we have chunks of our population that we know are going to be representative of the population as a whole. So those are called clusters. So for example, a mentor group in the Gray House might be representative of the Gray House as a whole, or the high school of the Gray House, for example. Like a high school mentor group might represent the high school members of the Gray House. It might be representative of them. It's a cluster of the population that is similar to the population as a whole. So a cluster sample is when we identify these clusters, these groups that are similar to each other and each representative of the population, and then we randomly select one or more of those clusters to take a census of. If I want to know the opinions of the Gray House about the House meeting, maybe I will just randomly pick 2 mentor groups, and I will take a census of each of those mentor groups. That would be a cluster sample. A multi-stage sample is when we combine one or more of those methods, and we break them up into strata, and within each strata we form clusters, and we census those clusters. That would be a multi-stage sample. So it's just combining multiple methods into one. And a systematic sample is when we survey every 10th person, or every 50th person, or every 100th person, or every nth person from a list or from a line of individuals. Maybe I stand at the entrance to the school in the morning, and I count off every 20th person, and I survey that person. I go for the next 20th person after that, and I survey that person, and so on. I count off every 20th person. Then I'm taking a systematic sample. I'm systematically choosing at random, because I'm not controlling the order in which they're showing up to the front door, but I'm systematically choosing the people that are going to be in my sample. We will go over all of these with more examples in class. No matter how I choose my sample, there will always be sampling variability. Sometimes this is called sampling error, but we're not going to call it that because error implies that there's something wrong with it. Sampling variability is natural and it's unavoidable. There will naturally be differences between randomly chosen samples. If I take a sample of 100 people and I measure some value of it, it's going to be different from some other sample of 100 people that I could have chosen from that same population and measured the value of it. The statistic that I get from one sample is naturally going to be in some way different from the statistic that I would get from another sample, even drawn from the same population. Because of the random selection, I'm just randomly going to get people that are somewhat slightly different from each other. So the average height of 100 males that I've chosen in my sample is going to be a little bit different from the average height of the 100 males that I could have chosen in some other sample. So there's always going to be variability between samples. Often, we're only going to have one sample. And so we have to have a way of accepting that the statistic we get from that sample is not going to exactly be the same as the parameter for the population as a whole. And how we deal with that discrepancy, how we measure how big that discrepancy is likely to be, is the subject of the entire second semester. But for now, we're just focused on taking good samples so that our data is meaningful and useful, avoiding bias, randomizing and selecting a sample that is representative of the population as a whole.